to, I guess this is our second webinar in our series for the NCSA Delta webinar series as part of the Exceed. My name is Greg Bauer. For those of you who don't know me, I'm a Senior Technical Program Manager at NCSA. I've been at NCSA for quite a while, and I've been involved in several projects. Probably the largest that I've been involved in is the large Blue Water supercomputer project, where I helped manage the application support for that. So hopefully if some of you were part of that process, you were on Blue Waters and got to work with members of the support staff there. But on Delta, I'm a co-PI in the project, and I'm working today with other members of NCSA's user services group that are also involved in Delta, Jay Alameda, who's coordinating things, and Sandy Kappas, who leads our training at NCSA. All right, let me advance the slide here. Whoops. A couple things we need to do before all Exceed webinars. First is to review of code of conduct. That's part of the boilerplate that we have to do for Exceed webinars. So if you find yourself in a situation where you feel that you're being targeted for any kind of issue related to race, age, ethnicity, national origin, language, gender, gender identity, sexual orientation, disability, physical appearance, political views, military service, health status, or religion, there are some avenues that you can to report these issues, these concerns. The code of conduct text here is reproduced on the Exceed website in the URL provided there. Today's organizer would be one of the contacts, Jay Alameda, and there are some Exceed ombudspersons who can help respond to any issues that you may have concern. And there's an anonymous reporting form with a URL on the bottom that would allow you to provide a means of reporting any issues or concerns that you have. The other slide here that we have to discuss is terminology. Exceed has a commitment to providing materials that are accessible and inclusive and show respect for everyone. And so we want to make sure that the content provided in today's webinar, the training materials, and the presentation abide by a certain standard. And so our statement here is to make sure that we keep language inclusive, and that no inappropriate materials, either verbal or written, are presented during today's webinar. So if you do have issues, you can let Exceed know through the terminology@exceed.org email address presented here in this slide. And of course, you can always reach out to the organizers of today's webinar as well. Before we get started, I'd just like to bring to your attention an upcoming webinar that we have not quite set the date for, but it most likely will be in December, but the date is to be determined. Hopefully early December, and that's going to be a session presented by technical staff at AMD, introducing the 3rd gen Milan AMD processor and discussing parts of the programming environment, the AOCC compiler and the AMD optimized math libraries as well. And so hopefully we'll have a similar session, hopefully the same hour and day of the week. And we'll send out notifications once we have the date firmed up, but hopefully it'll be the 1st or 2nd week of December. And finally, I'd like to introduce today's speaker. And Jay, are you gonna click the record button? Or do you wait till Max starts?
We are recording.
Oh, great. Okay, I didn't see a pop-up. All right, so today's speaker is Max Katz, who's a senior solutions architect from NVIDIA. And he's going to be presenting some materials on NVIDIA's software ecosystem for both the A100 and A40 GPUs that are going to be on the Delta system when it finally gets deployed and is operational. So if you haven't encountered Max before, Max has been providing a lot of training materials and working with people as part of some of the DOE projects through Argonne National Lab, for example, in Oak Ridge. So he has worked on systems such as Summit, which some of you might have already worked on, and also Sierra at Livermore, and is also involved in the deployment of Berkeley Labs' large Perlmutter system as well. So Max is a computational astrophysicist by training, who researched explosions of stars using fluid dynamic simulations. So some of you today might have some domain commonality with Max. Max got his PhD in physics from Stony Brook University. So Max, go ahead and take it away.
Thanks for the introduction, Greg. I'll go ahead and share. Okay, so I had to pick a particular set of topics to talk about today when it comes to the NVIDIA ecosystem. It's not an exhaustive list, and I know that this is a pretty broad audience. So please, if you have questions about things that I'm not talking about, I'm happy to answer them, but also I think we're happy to schedule follow-on sessions, whether they be part of this webinar series or whether they be like smaller sessions that are breakoffs from this on various topics. So please just let me know if there's something I didn't talk about that you're interested in. The NVIDIA ecosystem is really about accelerated computing. We are now in an era where you have plenty of accelerated servers that are there in supercomputers. Accelerated servers are servers that have both CPUs and GPUs, and CPUs are optimized for the serial parts of workloads and GPUs are optimized for parallel parts of workloads. This paradigm is something that does require you to think carefully about how you're going to use accelerated servers, especially if you've never used GPUs before. Part of what I want you to think about during this talk and after this talk is how would you go about rethinking about your application in this mode where you explicitly identify what parts of your calculation, whatever it may be, are serial and what parts of it are potentially parallel, and then go ahead and split the workload among the processors in your server accordingly. CPUs, by their nature, are latency reducing architectures, you might characterize them. So they're very good at doing specific serial workloads very quickly. They have, to benefit this, they have very large memory in terms of total amount of RAM. They operate at very fast clock speeds, and they have very large caches to supplement the main memory. And each of the cores is a fairly sophisticated instruction set that allows you to kind of predict ahead of time what kinds of operations you might be doing and then minimize the latency of any one operation. The kind of converse of that is that because the CPU cores are complex and general purpose, they are, in a sense, low efficiency in a per watt perspective. And if you are in a situation where you don't take advantage of the large caches that are on the CPU, for example, you might pay a penalty as well. Additionally, most CPUs, not all CPUs, but most CPUs today have relatively low memory bandwidth, which is relevant for many HPC applications that are memory bandwidth bound. Conversely, GPUs are about hiding latency. So every individual GPU core is a relatively low power core. It doesn't have as much of complexity as a modern CPU core, but what it makes up for that in is having lots of cores. So there's lots of computer resources, lots of memory bandwidth, and you do many operations in parallel. And then even though each one of those operations may be slower than the corresponding operation on a CPU, as long as you have a sufficiently large and parallelizable workload, you'll benefit from using a GPU. GPUs have the other drawbacks though. For example, they have relatively low memory capacity compared to CPUs. I mentioned that the low per thread or per core performance compared to CPUs is a factor. And also they have, in addition to low main memory, they also have smaller caches and smaller amount of memory per thread. And so that does pose an interesting challenge for many HPC applications they have to think about. When you're GPU accelerating workloads, you typically analyze your code and you figure out what fraction of your code, which could be a very small amount of code in terms of lines of source, are the compute intensive ones that are potentially parallelizable. You put those on the GPU, and then you take the rest and you put it on the CPU. So this is a very general idea for how to use GPUs and workloads. I'll get more specific in a bit, but I did want to set that tone that we're thinking about how to use GPUs for accelerating the compute intensive parts of your workload, the part where you have a very large for loop that could potentially be parallelized because the iterations are independent, those kinds of things. NVIDIA's A100 GPU is our top of the line data center, enterprise, HPC, whatever you want to call it, GPU for large scale HPC and AI artificial intelligence tasks. So it comes with 40 gigabytes of DRAM memory. That is small, as you know, compared to modern CPUs that have usually an order of magnitude more memory. On the other hand, it's our biggest GPU yet by this memory measurement. They have over 1 terabyte per second of memory bandwidth. So this is typically an order of magnitude higher than the memory bandwidths you can see on most high-end CPUs today. They have a number of features that are designed for accelerating HPC and AI workloads, and I'll go through some of them in a second. But two that are relevant are that they have tensor cores, which enable very fast matrix multiplication, which is relevant in many high-performance computing and AI domains. And also they have a custom interconnect called NVLink, which allows you to do very high communication on and off the GPU. And so those are a couple of key features of this GPU. I'll leave the specs of this processor up here on the screen. I don't want to spend too much time talking about hardware specifications today, but it's there for those of you who care more about these details. The main thing that is true about GPUs compared to CPUs is, as I mentioned, they have many cores. The cores are individually not that powerful, but the power of the chip comes from how many cores there are. These cores can do standard math that you might see in HPC, and then they also have some custom math that is more common in AI, and that HPC developers are now figuring out how to go back and use in their own workloads. Like I mentioned, it has about 1,500 gigabytes a second memory bandwidth. You can see the FP32 and FP64 throughput measurements, and also tensor cores, which I'll mention in a second, allow you specifically for matrix multiplication workloads, allow you to get a high amount of acceleration for those workloads. They have to be targeted to specific kinds of instructions or math. So you do have to do something like a matrix multiplication or something that can be cast that way, like a convolution. But if you can cast your algorithm in that way, you can benefit from the acceleration of these components of the hardware. I'm not going to focus too much on this diagram either. The main thing that I want to emphasize by showing you kind of a schematic diagram of A100 is just how large it is. A modern CPU core, or modern high-end CPU, single socket or dual socket CPU server, can be thought of as having, tens or maybe 100 of order 100 CPU cores. And it's hard to draw an analogy between CPU cores and GPU cores, and one could have a debate about what the difference is between them. But in terms of the units that do floating point or integer computation, there's thousands of them on modern high-end GPUs compared to tens or maybe 100 on CPUs. And so that kind of expresses the main difference between a CPU and GPU, is just how many more cores there are, units there are for floating point and integer math. Each one of the cores on or floating point units or arithmetic units on a GPU is part of a unit called an SM, or streaming multiprocessor. And there's many of those on a modern GPU. So there's 108 SMs, streaming multiprocessors on an A100. And the main difference, to kind of first order between GPUs of different generations, both at NVIDIA and then other GPU vendors, is how many of these SMs there are on a chip. And so the more of them we put on a chip, the bigger and more powerful the GPU is, and then the fewer, the less powerful, but also potentially less expensive to purchase, of course. And then we have different architecture generations where each SM unit itself also then improves from generation to generation. So this A100 belongs to the NVIDIA Ampere generation of GPUs, but if you've used the NVIDIA platform before, you may be familiar with previous GPUs like the A100 for the Volta generation, which had maybe a smaller number of SMs and slightly different architecture, but the same idea holds, that in each generation, we're trying to make the GPU bigger by stamping many of these together on a chip and making the chip wider, essentially, which is different from the old paradigm of how CPUs used to get faster, where you would make individual cores faster by running at higher clock speed, that sort of thing. We still, of course, focus on those things, on making individual computations more efficient. It's a big part of what NVIDIA does and what other GPU vendors do. But most of the change in modern HPC is about making processors wider. So that's why parallelism is such a key thing, right? There's so many cores on this GPU that if you cannot expose a massive amount of parallelism in an application, it's hard to use this kind of thing effectively. As an example of what is possible with some of the specialized hardware on GPUs, I'm showing here a measurement on A100 of matrix multiplications, both for kind of various precisions. So you're probably familiar, if you're doing HPC for some time, with single precision and double precision, right? FP32 and FP64. And you know that those are kind of the standard workhorses of high performance computing. But that's not, the game has changed in many ways. And the game has changed largely because of artificial intelligence. AI workloads can often benefit from low precision or lower precision math than HPC traditionally has. And that presents a challenge to HPC developers because it means that many of the new features in these chips are targeted toward AI and not HPC. And I'll come back to AI in a second for those of you who care more about that. But I just wanted to make the point that the benefits here are largely targeted at the AI audience, and then the challenge is on the HPC audience to figure out, how do I take advantage of these new features? Well, one thing that you can do, of course, is just run your calculation in lower precision. And if you believe that you can get away with that loss in precision. And so the chart on the left here shows you what you can do if you take advantage of lower precision math. So for example, if you do a matrix multiplication in single precision FP32 math, you can benefit from up to an order of magnitude more improvement in the throughput in terms of like teraflops per second for large matrix multiplications if you use, for example, 16-bit arithmetic, and that's what we're showing here. You can also get a kind of middle performance, like a factor of 5 or 6 or something like that, in increase in performance, if you take advantage of this new precision mode, TF32, which I'll get to on the next slide, and I'll mention, and so I'll discuss what that is about. But the key thing here is that various approximations to the kinds of calculations that people do are now becoming important in understanding modern architectures. And so it's worth thinking about, if you've just been doing FP64 for your whole life, can you benefit from these things, right? You will lose some precision, but you may benefit from very large speed up. And so it's worth carefully thinking about that. Also on A100, for the first time on NVIDIA GPUs, tensor cores, which again I mentioned accelerate matrix multiplication workloads, can now benefit directly FP64 arithmetic. And so, at least on paper, the theoretical performance of an FP64 matrix multiplication with just standard, FMA instructions, it's about 9.5 teraflops, and that's pretty, good performance. But you can double that performance if you take advantage of tensor cores, because for the first time with these A100 GPUs, tensor cores can do FP64 math. And so again, if you can express your algorithm as a matrix multiplication, there's lots of ways to benefit from these modern GPUs. Of course, not every algorithm does that, but I would still argue that these GPUs are pretty good for many kinds of HPC workloads. So I won't talk too much about this, but I'll just mention as one example of the new kinds of calculations people are doing. TensorFloat 32 is a precision that NVIDIA came up with in part of this generation, which has the numerical range of FP32, but the precision of FP16. So it allows you to express calculations where the numbers are fairly large in some sort of absolute terms, but where you don't need that many points after the decimal place to express the precision of your number. We use this by default in AI training, for example. If your data is in FP32 format, which is a pretty common way to start for deep learning training, for example, then just by default, out of the box, our GPUs will use this TF32 mode for accelerating the performance of the matrix multiplies that occur as part of the convolution operations in a typical neural network. And so that works for many machine learning workloads, which don't need exact answers, but are okay with some level of approximation. But you can also take advantage of this in HPC. So as an example of the kinds of things that we're doing in HPC, you could imagine taking a problem like an iterative solve of a linear system that is originally starting with FP64, FP32 data. You could imagine doing a first approximation to the solve in a lower precision, like FP16 or FP32 or this TF32 mode, and then iteratively refining that answer until you get the same precision answer that you would get, that you would have done if you had done the whole calculation at FP64. And NVIDIA has shown that you can speed up these kinds of solves by a factor of several in many cases by taking advantage of this lower precision. Again, you get the same answer at the end to at least IEEE precision, but under the hood, it's doing these mixed precision calculations to take advantage of that. And in our cuSolver library, which does these kinds of linear system solves, we do that automatically for you today. Again, Another thing that's interesting about GPUs that we're constantly innovating on when it comes to, for example, AI workloads, is the notion that you may have some part of your calculation that you know is sparse. And that comes up very frequently in AI training, where you train a neural network, and then many of the weights in your neural network are small or even close to zero. And therefore, if you were to prune them from your network, they wouldn't change the answer much. Well, NVIDIA's A100 GPU can actually define a sparsity pattern where 2 out of every 4 weights are treated as 0 because you did the calculation, you went through your weights and you determined that many of them are close to 0 and can be ignored. And so therefore we can effectively double the throughput of a like a AI inference calculation by just skipping the numbers that are close to 0. And that will give you much higher throughput. Of course, there's some potential loss in accuracy if your approximation wasn't that good, that these weights are 0. But as long as you did a good job identifying those, and we have some tools to help you do that, you can get 2x faster throughput, essentially just by skipping the zeros in your calculations. And that can lead to, for overall speed ups, a factor of up to 1.5, for example, on something like BERT. A100 also has the ability to do both logical and physical partitioning of the GPU. So you can have many workloads running on the GPU, for example, many MPI ranks running at the same time on the same GPU. And also it's possible to physically partition the GPU so that you have individual slices of the GPU that are completely isolated from each other. If you want like a defined quality of service for getting essentially 1/7 of the GPU, but then including all of the things that go along with it, essentially 1/7 of the memory, 1/7 of the throughput, but then you get that slice of the GPU is all yours. And so I think we still have to figure out the details of how something like this might show up on Delta, but you can expect that this will be something we're very interested in figuring out, is how to make this kind of thing available to you if you have workloads that can't use a full GPU, but can at least use some part of the GPU. And also, in addition to A100, we have, so A100 is our kind of high-end HPC/AI computation GPU. It's really for big workloads, large parallel workloads that are primarily doing math-intensive operations as their main thing. We have several other GPUs in the Ampere generation of GPUs. A40 is another example of that you'll also be getting as part of Delta. And you can think about A40 as a GPU that's more targeted for visualization workloads and other data science and other data-intensive workloads. So it uses the same generation of cores. Any application that you write that can target A100 can also target A40, but it also has some different characteristics that make it more applicable for like data science or visualization workloads. So for example, it has RT cores, which accelerate ray tracing operations and can be used for real-time visualization of scientific data. It has the tensor cores like we discussed, but in return, it doesn't have double precision math, really. You wouldn't do like a FE64 calculation on this GPU. You would do that on A100. But it's primarily designed for kind of lower precision calculations, things like visualization where like you don't need that many digits of precision. A40 is interesting in that it has a very large amount of memory, and so that can be used for compared to many other like workstation or consumer GPUs anyway. This can allow you to fit very large data sets in the GPU for processing, for data science or for visualization. And so this will be a good workhorse GPU for those kinds of workloads. This is a good time for me to pause and see if there are any questions, because I'll switch to software next.
Great, thanks, Max. Looks like there was one question initially, but William seems to have said that the answer was in your slides. First, it was basically, can you comment on the FP64 tensor core throughput for the A100, which I think maybe you addressed.
Yep. Yeah, basically it's a factor of 2x if you can use it.
Let's see here. You mentioned about support for partitioning, and we do have plans for supporting the A100 partitioning. Jiansen, will the slides be available somewhere? And I believe, yes, we will make the slides available, and we'll send out a note when that is, and possibly the recording as well. And Sean asks, what are the options for A100 memory configurations?
A100 ships in 2 variants. It has a 40 GB memory variant and an 80 GB of memory variant. I didn't talk about the 80 gigabyte one in this presentation, mainly because it's not, you don't see it in that many places. Primarily, it's used by like large AI enterprises that need to get like the absolute top performance, and they need to fit like very large models. So it's not a common configuration that you see in like HPC centers. Pretty much all the deployments that I'm familiar with in HPC are using this 40 gigabyte variant. So that's why I chose to mention that. But indeed, there is an 80 gigabyte memory variant. Other than that, the A100s are the same, essentially. Whether they have 40 gigabytes, 80 bytes, just a difference in memory and also memory bandwidth that goes along with it. Were there any other questions?
Yeah, there's a comment here regarding using MPI multiplexing. So oversubscribing a single GPU with 36 MPI ranks would lead to poor performance compared to 9 MPI ranks using a strong scaling test. Can you comment on that?
Yeah, the main thing that I like to emphasize whenever we talk about using multiple ranks, for example, on the same GPU, is going back to my point that fundamentally GPUs work best when you're doing a large parallel workload. So in some sense, the ideal way to run a GPU is always going to be a single rank per GPU with just a large amount of work in that rank, right? So if you solve like a computational fluid dynamics problem or a molecular dynamics problem or some other problem that kind of expresses a natural decomposition of work, right? Where some number of elements in a simulation can be mapped to a particular GPUs, all else equal, you'll want to put as many of those as can fit on the GPU, for example, subject to the constraints on how much memory is available, because that will allow you to maximize the likelihood that you're saturating the throughput of the GPU. There's so many cores on the GPU that unless you have a lot of work to do, you won't be getting full benefit from it. Now, there are some reasons why you can't always do that. And so there are constraints there. And so some people will then choose to use multiple ranks on the same GPU to take advantage of the fact that for whatever reason, they can't refactor their application to be written in that mode. And it's definitely true that if you try to run a large amount of ranks per GPU, you may not get optimal performance compared to the other scenario where all of the work is on a single rank. There's multiple reasons for that, including that it consumes more memory on the GPU and each individual piece of work that you launch on the GPU may be less efficient. So I agree that 36 ranks per GPU, it's not impossible to make that work well, but it is challenging. And so it's worth thinking about. I'm happy to talk to anyone about offline about how to optimize those kinds of workloads.
Okay, great, thanks. We can continue on now.
Okay, so how do you use these GPUs? How do you program them? Well, in HPC, NVIDIA provides the NVIDIA HPC SDK, which is a package that essentially gives you all the tools that you would need to program on the NVIDIA platform. So it includes C and FORTRAN compilers and C++, of course, for targeting both multi-core CPUs and GPUs. It has a set of math and communication libraries for accelerating various workloads. And it also includes the tools that you would need for analyzing the performance and correctness of your application. The NVIDIA HPC SDK is freely available. So you can download it on a workstation. In addition to, it'll be available on Delta as a kind of core way that you can use GPUs. This is not the only way to use GPUs, right? We do recommend that you use the NVIDIA HPC SDK for targeting the NVIDIA platform, but many other, open source tools and compilers are useful also. I just wanted to go through a couple of things that NVIDIA offers for targeting NVIDIA GPUs. We think about targeting or programming for GPUs as a multi-level problem. So you have to, of course, program for the accelerator or the processor itself. So some amount of your time is going to be spent actually optimizing a workload to run as well as you can on the processor that you're running on. And that will be both CPUs and GPUs in a modern accelerated server. There's also network concerns, right? So most workloads today benefit from being able to scale to multiple nodes. And I'm sure that many of you who are centers or users of NCSA, other sites, are familiar with that concept. So there's nothing odd about the concept of programming to take advantage of both the CPU, the GPU, and now additionally the network, but it does introduce some new ways of thinking about things because GPUs are so much faster than CPUs for many workloads that you may hit strong scaling limits in your application before you otherwise would. So I'll get back to that point in a second, but just sticking on how do you make the GPU component faster, we provide a couple different ways for you to take advantage of GPUs. for accelerating your workloads. The way that we would typically recommend that you start is to use the high-level features offered by the languages themselves. So for example, in C++, as of C++ 17, there are multiple parallel algorithms that allow you to express different kinds of parallel algorithms directly in the language. And so for example, you can perform operations on vectors or arrays that transform them or add them together, perform a reduction, that sort of thing. So std, transform, std, for each are examples of these algorithms in C++ 17. And NVIDIA's NVC++ compiler allows you to write ISO standard, ISO compliant C++ code that can target both multi-core CPUs and GPUs using a single language that has no GPU specifics at all. And so I've given you an example of that on the top left of this slide. Similarly, in FORTRAN, as of FORTRAN 2008, you can use the do concurrent construct, which allows you to write iterations of a loop that have no logical dependence on each other. And NVIDIA's NVFortran compiler can accelerate those loops so that they run in parallel on a GPU. And I'll come back to this in a moment, but we also have the ability now to accelerate Python workloads as well, so you can write basically standard Python using NumPy and accelerate that on GPU. Now, those give you the most portable workload, most portable source that you can have. So it allows you to write one piece of code that can potentially run anywhere, as long as there's vendor support for acceleration on that platform. Sometimes you need to optimize your workload to target a specific processor, or because you want to get you want to do some operation that the standard language doesn't yet have the flexibility to do. So we provide also directive-based approaches like OpenACC and OpenMP that allow you to give hints to the compiler to accelerate your workload. You identify particular parts of your code and you tell the compiler, hey, I want to do this parallel operation at this point, and the compiler figures out what the best way to do that is. So we provide those programming models. And then at the lowest level, if you really want to get maximum performance out of the processor, you can use a language like CUDA that allows you to get maximum performance. You have to do more work because you have to identify what each thread is doing and then assign work to those threads. And it gives you much more power, but also, with that power comes the additional workload of responsibility of assigning work. But it does give you ultimate flexibility for optimizing performance on a platform. We provide, of course, several libraries to accelerate standard workloads. So you know that if you're doing a matrix multiplication or a linear system solve, you'd always use the vendor library or the system provided library to do that. And that's no different on the NVIDIA platform. We provide several math libraries to accelerate standard kind of operations. So like BLAS and LAPACK operations, we have corresponding libraries, CUBLAS and QSolver, in the NVIDIA portfolio that you can use for those. And again, those come freely available as part of the NVIDIA HPC SDK. Of course, FFTs and random number generation are also standard things people do and are part of our math library suite. And then in the C++ language itself, we support several modes of things that are similar to the standard library. So thrust allows you to perform operations on STL vectors. And more recently, libcu++ allows essentially some part of the STL to become available on within GPU code as well. And then we also have cub, which expresses parallel performance primitives like reductions within a GPU. So we make these available again as part of the HPC SDK, as part of CUDA. So coming back to this communication point I mentioned, when you do get your GPU workload accelerated, then you run into a situation where now the compute part of your workload is so fast that you may need to have very high performance networking for that. So NVIDIA provides several communication libraries as part of our collection of software to help you address this. HPCX is a package that includes OpenMPI and other parts of the and UCX and other parts of the messaging stack that allow you to get high performance message passing, both between CPUs and also using data buffers that live on the GPU using CUDA aware MPI, if you're familiar with that. And so you can use standard MPI. You can also use other programming models. So Nickel, the NVIDIA Communications Collective Library, is used often by AI workloads to do common reduction or parallel collective operations. So for example, all reduce is a common thing that occurs in deep learning workloads, but of course also many HPC workloads. And so Nickel gives you high performance direct communication between GPUs for those operations. And then NVSHMEM is a PGAS language similar to based on the OpenSHMEM standard that allows you to do communication directly within a GPU kernel. So if you want to talk to from one GPU to another without coming back to the CPU, NVSHMEM will allow you to do that. Here's just a summary of HPCX. Again, it's basically a high-performance implementation based on OpenMPI that we believe is well accelerated for NVIDIA systems. And so you'll see more about this later. But again, it's just part of our HPC SDK and allows you to take advantage of MPI implementations that are best optimized for our platform. So saying a little bit more about this notion of doing calculations directly within a standard language. What we recommend today as the first step for getting people who are using GPUs for the first time, if you're writing C++, is just use the standard language itself. So this is an example from the LULESH benchmark, which is a unstructured grid hydrodynamics benchmark from Livermore Lab. And we've given you a snippet of code here that's basically taking a particular part of that calculation that calculates a time step. And we're showing you on the left the original code from the benchmark, which was parallelized with OpenMP. And then on the right, we have the same code, which is parallelized using standard C++. So you can see it uses this concept of stood transform reduce, which is one of the C++ 17 parallel algorithms. It allows you to write more elegant and compact code, but it also allows you in particular to write more portable code. Because you may be familiar, if you've wrestled with the concept of using different kinds of processors before, that if you're writing code that needs to run on both CPUs and GPUs, then you run into the problem of, well, what programming model can I choose that targets all of these things, right? And there are some things that do, or at least promise to. So you may be, OpenMP sort of does, but OpenMP has a mode that is kind of more targeted for CPUs, and then the target construct, which is kind of more targeted for GPUs or accelerators. And using both of those in the same application is not impossible, but it's certainly something that I think the community is still learning how to do. Similarly, OpenACC provides a model that allows you to run on both CPUs and GPUs, and so these things exist. But one, I think, compelling alternative to this is, again, the standard languages themselves. And so you can write this code that can be chosen at compile time, whether it's targeting CPUs or GPUs, and you can use it. And it's portable because it's in the standard language itself. And so any compiler that implements a parallel backend for these operations can then be used on their platform. Here's an example on this benchmark on comparing the performance of the A100 to a kind of high-end Intel server. And what you see is that if you use all of the cores on this CPU server, and then you compare that to A100, you can get a factor of 7x improvement just by using the ISO C++ code. And again, I want to emphasize that basically with the same exact performance that you would get using OpenACC or a more highly tuned implementation. So you can write portable C++ compiling code that gets a pretty significant speed up compared to CPU servers. Similarly, in FORTRAN, we have a couple modes that are available for taking advantage of accelerated FORTRAN. So one example is that, in FORTRAN, those of you who are FORTRAN users are used to the concept that you have nice intrinsics that do many things for you. And so that if you're writing FORTRAN, typically you're not going to write matrix multiplication explicitly. You can just use the matmul intrinsic, and that's a very nice benefit of using FORTRAN. Well, if you were going to do this in a lower level program model like CUDA or OpenACC, you might be tempted to write out the loop explicitly and then assign parallelism, right? And then that gets into the problem where in order to take advantage of that, you've done the thing that that you shouldn't be doing, which is writing a matrix multiplication by hand. So one thing that NVIDIA can do for you with NVFortran, our FORTRAN compiler, is that we can accelerate many intrinsics in the FORTRAN language, taking advantage of our cuTensor backend. cuTensor is one of the math libraries we provide that accelerates matrix or tensor operations. And then we can actually map those directly to the tensor cores on the GPU. And so, for example, we have a plot here on the right of our previous generation of V100 GPU and an implementation of the an optimized implementation of the matrix multiplication, comparing that to A100. And basically, you can get a very large fraction of that peak theoretical 19.5 teraflops per second if you take advantage of this MATMUL intrinsic, because again, we can do all the magic in the back end of mapping that to a tensor core operation that can accelerate that workload. It would be very hard to do that writing the code on your own. And so that's a benefit from using the FORTRAN intrinsic. And also in FORTRAN, we have this notion of do concurrent, I mentioned. So do concurrent is a contract in FORTRAN 2008 that allows you to express a loop where the loop indices are not logically, there's no dependence between them. And we can actually compile this do concurrent construct to target both multi-core CPUs and GPUs. And that allows you to accelerate many common kinds of workloads. So as an example, this is a calculation that basically does an iterative smoothing calculation that you might see in a linear solve. And we're comparing, so the code on the bottom left shows you what it might look like, right? All of this is standard language FORTRAN. So you can see no NVIDIA constructs, there's no GPU reference at all. There's standard FORTRAN that expresses a loop that does some number of operations in a range of integer bounds. And we can automatically compile that to target a GPU backend. And then you can see a comparison of a dual socket Xeon server compared to A100. And you can get, a large factor of improvement, essentially a factor of 10 or more improvement by taking advantage of the parallelism that's available to you in the GPU. Of course, this has to be a very large parallel problem to take advantage of it. I'll emphasize that again and again, that you really need a large number of elements in your calculation or degrees of freedom more generally to be able to loop over in order to take advantage of a GPU. But if you can do that, you can get pretty nice parallelism out of a GPU. I think, and just to summarize then, you can write both in C++ and FORTRAN, you can write one section of code that can be targeted for either GPUs or CPUs. And so if you NVC++ or NV-FORTRAN, you add the -std_par flag, and that allows you to accelerate those. You can either target multi-core CPUs or GPUs. And so just by changing a compiler flag, you can have one piece of code that runs on a platform that's of interest to you. This would be a good point for me to pause and ask if there are any questions.
Great, perfect, Max. We got two. First question is the GPU auto-parallelization for C++ and FORTRAN specific to the NVIDIA HPC SDK stack? That's the first question.
Right, so no. The whole notion of these constructs in the language is that the language allows you to perform a high performance implementation of these that can, as long as it respects the semantic constraints of the language. So with both do concurrent and like std transform, the language itself doesn't actually say like you should or should not run on multi-core CPUs or GPUs. It just says, semantically, these things can be run in parallel, and then the compiler can perform whatever optimization it wants to do that. And so on the NVIDIA platform, of course, because GPUs are such a large component of how we believe HPC can get high performance, we provide the ability to do both multi-core CPUs as well as GPUs. But there's nothing about it that requires the NVIDIA software stack, because again, this is just standard FORTRAN or C++. Now, not every compiler that's out there has implemented this in practice, right? And so not every compiler or vendor will have an implementation of do concurrent or std transform that runs both on CPUs or GPUs, or if they do, it may not be equal performance or may not achieve a high implementation of performance, right? Or a high fraction of peak performance on those platforms. But I think that you can be confident that, first of all, there are most of the modern compilers have at least some implementation of this already, at least on multi-core CPUs. And because these are part of the language, I don't really see an outcome other than that every vendor adopts this. And so I think that this is a good forward-looking way to start thinking about your code, because there's really no way for vendors who haven't done this yet to avoid doing it. Because again, it's there in the language. And so it's just too compelling of an option not to have implementation for all platforms.
Okay, great. And then I guess in that context related to auto-parallelization, how do you manage the data movement between device and host when using these language features?
A good question. One of the things that, so if you've used GPUs before, you may know that, and I mentioned this before, but GPUs have a separate memory space from CPUs, right? You have the CPU RAM, you have the GPU RAM, Those are physically distinct memory spaces on the server. And so a result of that is that memory management does become a key factor in GPU workloads. The GPU is optimized for high bandwidth to its own RAM, right? And if you are accessing memory that's on the CPU, you're going to have to go over whatever bus is connecting the CPU and GPU. Typically, on most server platforms is PCIe, right? And so that's a factor of 10 or more in bandwidth between what the GPU can get if it's talking to its own RAM versus what the GPU can get if it's talking to the CPU. This can be a complex thing to work with, and one thing that NVIDIA provides to help manage that complexity is this concept of managed memory. So a managed memory allocation is one that can reside on either the GPU or the CPU and can automatically migrate back and forth between those two processors. So if you allocate some memory in this managed memory, and you touch it on the CPU, then if it's already on the GPU, it'll migrate from the GPU to the CPU, and then vice versa. If the memory is needed on the GPU, it's written to or read from on the GPU, and it's currently on the CPU, it will probably migrate from the CPU to the GPU and then be read there for highest performance. And so dynamically, during the run, it'll move back and forth to be where it needs to be. This is available in pretty much all of our program models that we provide. And one thing that we did to make quality of life nicer when it comes to using standard C++ or FORTRAN is that we automatically take all dynamic memory allocations in your application and then use this managed memory for them if you're using the stdpar operation. So anything that looks like a malloc or new in C++ or like an allocate statement in FORTRAN will automatically opt into, if you're using the stdpar flag, will automatically be replaced with this managed memory allocation, and they can migrate to wherever it needs to be. And you can also opt into that mode in other program models too, if you want to take advantage of this nice feature.
Okay, great. Looks like you answered the next question with this slide here. Are FORTRAN intrinsics run only on the GPU when you enable standard par equals GPU? And I think the slide clearly shows that.
Right. Today, it's basically you pick one or you pick the other, and you pick which one you're compiling on based on the time. So if you're running on a GPU server, it doesn't really make sense to target anything other than GPU for doing like a matmul, right? And so you would typically accelerate everything on the GPU. And then if you just take that same code and run it somewhere else, you then just recompile with stdpar equals multicore.
Okay. All right. Next question is a Python question regarding CNumeric, the CNumeric library. Would that run on other NVIDIA GPUs, say the NVIDIA T600?
So I'll come back to, I'll say a brief slide on CUBLAS in a second. But one thing I want to emphasize is that NVIDIA essentially has one architecture everywhere. All of these models, program models that I'm talking today, at some level, sit on top of the base CUDA language or program model, you might say. And so one benefit of that is that any code that can run on one NVIDIA GPU and essentially any other NVIDIA GPU that has been released for the last decade, essentially. Of course, there are new hardware features and new generations, right? So if you write some code that intentionally targets new hardware features from A100 and then try to run it on an older GPU, like a Turing class GPU, then yeah, that'll, you may have to have some backup path for that. But in general, any code that does kind of standard math that has been on our GPUs for generations now, you can just run that same code on A100, you can run it on T4, you can run on RTX 3080, right? Any of these GPUs, we have one base platform, one common CUDA level that sits underneath all of these. And so the idea is that you can have one code that runs on basically any NVIDIA GPU. That's a core part of our platform. We're never going to change that.
Okay, great. So I know it's 11 minutes before the hour, and we have a few more questions, but how much more content do you have to present versus maybe some of these questions we could possibly take after you wrap things up?
I'll provide like 2 or 3 more slides really quickly, and then we can have some last questions, if that makes sense.
Okay, great. Thanks.
So I have a couple of slides here on profiling tools. I'll skip through them in the interest of time, but they're there if you want to talk about them. I just want to say a couple of words about non-HPC things. So we care a lot about accelerating data science and machine learning. And so the Rapids tool set is a set of libraries that are basically GPU accelerated versions of things that you're already familiar with for data science and machine learning. So basically, if you're familiar with scikit-learn or pandas, we basically have those on GPUs. We have different names for them, like cuDF for Panda, and then cuML as a replacement for scikit-learn. But they're intended to take the same APIs that you're familiar with and then accelerate them on GPUs. And so many data science workloads can benefit from essentially out-of-the-box improvement on NVIDIA platform. And I'm sure that we will have a more in-depth discussion on this point in a later presentation for this audience. So this is not the last time you'll hear about it, but I did want to make it clear that there's plenty of ability for you to perform those kinds of workloads on GPUs. And this new thing, Legate, that we introduced, allows you to take essentially standard Python code using NumPy and accelerate it both on individual GPUs and many GPUs. So you can take standard NumPy code, and instead of import NumPy as NP, import QNumeric as NP, and then accelerate that natively both on a single GPU or across a whole cluster. And we've demonstrated that this can be used both within a single server, as well as essentially all of Summit, the largest GPU supercomputer in the US, and scale many workloads that way to very large numbers of nodes. So this is new, right? We're still kind of working things out, but it's open source. It's available on our GitHub. Go and download it now if you want to try it. I think this will be a key thing of what we experiment with on Delta, is getting people trying this and seeing if it's a useful thing for your workload. And then finally, I'll say that, I didn't really talk about deep learning like TensorFlow and PyTorch today, and we can have many discussions on that point. But one thing that I want to emphasize is that these frameworks just work on NVIDIA GPUs. So if you're familiar with using TensorFlow or PyTorch or MXNet on targeting CPUs, essentially you can write the exact same code and just use the GPU backend of these frameworks, and you're good to go. And we provide on ngc.nvidia.com a catalog of optimized containers for using machine learning and deep learning workloads. So it includes the Rapids stack that I mentioned before, as well as the deep learning frameworks. So you can just download these and get our optimized implementations of these frameworks that we think will work really well on A100 and A40, as the case may be. And we will make these available on Delta essentially through Singularity, so you'll be able to run these. And this will be the recommended way to run machine learning and deep learning models on the NVIDIA GPUs on that system. And I'll just leave this here and mention that there's many things that you can get on the site that benefit from both pre-trained models in deep learning as well as the frameworks themselves. Okay, so I think that I should stop there, and we can have any last questions there were.
Great, thanks, Max. And as a note, we are planning to make things like the NVIDIA container maker and access to the pre-built containers for all those machine learning solutions available on Delta. All right, so let's continue on. We got a few more questions to fit in. So one of these is, based on your experience, what level of parallelism is considered large enough to benefit a GPU? A do loop of 1 million?
One way to think about this question is to think about how many threads a modern GPU can have in a flight. The modern GPUs like the V100 and A100, that number is of order 200,000 or so. That's kind of how many threads you can have on one of these GPUs at one time. And so not every workload will be able to use all of those threads in flight at one time, but that is the upper bound. And so if you have a workload which has a do loop of length 1 million, yes, you have a pretty good chance of saturating a GPU for that. But if it's much less than 1 million, that starts to become risky, and you may not get full benefit out of a GPU from it. So yes, you have to think very large in terms of using a GPU effectively. Do loop of length 1,000 is not great for running on a GPU, and you might want to think about whether you can either just running that on a CPU, or whether you can like aggregate bits of work into one larger loop that can benefit from the amount of parallelism that's available on a GPU.
Okay, and this one I kind of lost the context. So Ron, I don't know if you want to re-ask the question, but it was regarding the use of intrinsics like matmul. And I don't know if the context was with standard par or language standards exactly. I kind of lost track where that fit into the slide deck. So Ron, if you want to unmute yourself, you can ask the question if you're still there.
Hi, can you hear me?
Yep.
Oh, the question is like, so for do concurrent and things like that, you put, standard power equals GPU to activate it. And I know like if you have an open ACC loop and you have matmul inside that loop, it'll run that on the GPU. But the question is, what if I have a matmul sitting out there or a maxval or something like that? If I do standard power equals GPU, will it try to do that on the GPU and automatically transfer data, or
right,
I have to decorate it?
Right. Tested par is the flag that also allows you to opt into this automatic GPU acceleration of intrinsic like matmul.
And that covers all intrinsics?
It's not literally every intrinsic that exists. I can give you a more complete list. I didn't bring the slide with me, but there's basically most matrix operations or anything that looks like a matrix operation, we can map to some aspect of cuTensor and therefore can accelerate. But there are other things like maxval, for example, is not something that I believe today we have an implementation of and would be perhaps more better done using do concurrent or something like that, because there are reduction things coming to FORTRAN standard that would support that.
Right. Yeah, I think maxval might be support, but max lock is not, or something like that.
Yeah, we can.
Yeah,
I can provide a more detailed list offline.
Okay, great. I think we might skip. It looks like there was a question from Roland Haas about something about triggering transfers, but I think that was answered by some members of the attendees with some documentation from the NVIDIA website. So maybe we'll jump ahead to a question from Greg Childress here. He says, I see there are experimental integer tensor ops, but currently the only accumulate op appears to be POP-C. Are there plans to expand the options to, for example, XOR?
This is actually not the first time I've seen this question, but it might be the second. It's something that we thought about. And for us, in many cases, the answer is, well, the hardware supports what it supports. And then in other cases, it's just a question of we need to do some work in the software to enable such a thing, or present it as a aggregate or like a combination of things that are native hardware instructions. So basically, if there are some feature, like some hardware instruction or software instruction that you would like that we don't have today, I think the best way for you to see if we can make that happen is just to email me, and I can send that to our product manager for math libraries and let him know. And as long as you present a kind of compelling use case, we're happy to discuss prioritizing that accordingly. So I mean, the short answer is I don't know that we're going to do that specific one right now, but it's kind of on our radar. And if you tell us that you need it, it's useful information.
Okay, great. That's all the questions I think we have, unless Roland, you don't think the information that other people provided was sufficient with using CUDA mem advise for initiating early transfers of data from host to device, I guess, or device to host. Okay, he says he's good. All right, great. I know you kind of glossed over some of the tools and other parts of the ecosystem. I think we'll try to arrange at a later date, once Delta is in production, some additional more in-depth webinars focusing on the tools, since they're really exciting and interesting and makes life a lot easier. So thanks again, Max. Jay, do we have any closing comments from as the organizer?
No, except thank you to Max and you, Greg, for hosting this. Very much enjoyed this session. Thank you very much.
Thanks. We did have one quick question from Ron again. Is there an ETA for the, I don't know what EUP is for the Delta GPU? What's EUP? Estimated early user. Yes, no, we're still working on that. As many of you know, there have been some supply chain delay issues, and so we're still working on finalizing that schedule. So once we have a better idea of when staff are going to be able to get on the system and make it available for early user program, then we'll let you know. All right. Well, thanks everyone, and be on the lookout for our next webinar, which hopefully we'll have sometime in early December. And hopefully we'll have additional information to provide on updating schedules. So thanks again for everyone joining. Have a good rest of your day.